Comparison of the expected rewards between probabilistic and deterministic analyses in a Markov model. This presentation is based on our publication in the Expert Review of Pharmacoeconomics and Outcomes Research. The outline of this presentation. I will start with the background. Probabilistic analysis is termed as probabilistic sensitivity analysis. In recent years, there has been a shift in economic modeling from the use of deterministic analysis to probabilistic analysis for evaluating the cost-effectiveness of healthcare technologies. Deterministic analysis considers only the expected values of model inputs, that is, point estimates of costs and clinical inputs. Probabilistic analysis considers model inputs as probability distributions to account for parameter uncertainty. From a policy perspective, it may be important to not only generate results as point estimates, deterministic, but also understand the uncertainty associated with the results, and ultimately the decision being made. Recently, some guidelines state that probabilistic analysis provides best estimates and less biased estimates of costs and outcomes compared with a deterministic analysis in a nonlinear model, such as Markov model. This encourages the use of the probabilistic approach over the deterministic approach. Guidelines from some institutions recommend probabilistic analysis not only for sensitivity analyses, but also for the reference case to estimate the expected cost and clinical outcomes. We sought to understand why probabilistic analysis is less biased than deterministic analysis in the Markov model. We considered the references provided in the guidelines and also conducted a literature search. Although several publications discuss the advantages of probabilistic analysis over deterministic analysis, we did not find any simulation studies that compared the performance, bias, and accuracy of the two in estimating the expected cost and effectiveness in Markov models. To better understand the performance of both the probabilistic and deterministic analysis in a Markov model, especially when model input parameters are informed by weak evidence, we conducted a simulation study and compared these two analytical approaches for estimating important Markov rewards such as expected life years. There is an interesting phenomenon. Favorable results are often based on weaker evidence in probabilistic analysis. For example, a model input that uses a treatment effect derived from weak evidence, based on a small sample size, generally leads to misleadingly favorable results in terms of life years and Cowley in a probabilistic analysis. We illustrate this in an example below. We developed a simple Markov model that included three states: healthy, disease, and dead. All patients are initially in the healthy state, and only one-way transitions are allowed in the model. People can only move to worse health states and cannot move back to better health states. Thus, there are three possible transitions. 1. From healthy state to disease state. 2. From healthy state to dead state. And 3. From disease state to dead state. We assumed the transition probabilities are constant. We used the duration in the surviving states, life years, as the reward. We set the cycle length at 1 year, the time horizon to 100 years, and did not apply discounting and half-cycle correction. Using this model, we compared different treatments that have the same expected value of model inputs, but were obtained from the clinical evidence with different cohort sizes, 100, 1000, and 10,000. The distributions of model parameters are shown in the table. This density plot showed beta distribution data with the same expected value and different sizes of cohorts. The evidence from the small sample size evidence, the left plot based 100 patients, has a greater variance than the right plot from 1000 patients. To better understand the findings, I suggest that you pause this video and spend a couple of minutes developing the models on your computer. Now, let us review the findings. The Markov rewards in probabilistic analyses were greater than that in the deterministic analysis. The Markov rewards in life year were greater when the distributions of model inputs are defined from the weaker evidence. When the sample size of evidence was large, such as 10,000 people, the probabilistic analysis and deterministic analysis almost showed the same results. Furthermore, the probability of treatment with weaker evidence having a greater reward was higher than treatment with stronger evidence in the probabilistic analysis. This section, Jensen's inequality, describes the reasons for the above finding. Weaker evidence is associated with greater rewards. In linear relationships, we can use a straight line to represent the relationship between the independent and dependent variables. For every unit of change in the independent variable, the dependent variable has a corresponding proportional change. This relationship does not occur in a nonlinear relationship, such as Markov models. Jensen's inequality, named after the Danish mathematician Johan Jensen. If a function is convex on an interval, for all x1 and x2 in this interval and 0 is less than or equal to lambda is less than or equal to 1, the following inequality holds. This figure illustrates the concept of convexity using a simple geometric interpretation. If a function is convex, the graph of this function is below the secant line. I provide some further read materials to evaluate convex or concave of functions. Elbasher and Chatwell characterized the conditions for upward or downward bias using a three-state Markov model and derived rewards, such as life years, Cowley, lifetime disease costs, using mathematical expressions for transition probabilities. Further, the authors demonstrated that life years and Cowley are convex functions of transition probabilities using Jensen's inequality. Mercer then extended Jensen's inequality, as shown below in this slide. Based on Mercer's inequality, we can deduce that life years and Cowley estimated using probabilistic analysis are greater than those using deterministic analysis. Let x be the transition probability and function, x, be the life years in a Markov model. Let us assume that n samples are simulated in the probabilistic analysis, and let each simulation have the same weight and the sum of weights equals 1. When n is large, the left side of inequality represents the expected rewards in the deterministic analysis. The right side of the inequality expression is equal to the average reward in the probabilistic analyses in n simulations. Then, we can conclude that the rewards in life years and Cowley of a Markov model from deterministic analysis are less than those from probabilistic analysis, irrespective of the distributions used for transition probabilities. When model inputs are obtained from strong evidence, the parameter uncertainty is small and is concentrated around the mean value, so the rewards, life years and Cowley, derived from probabilistic analysis will be close to the rewards derived from deterministic analysis. However, if model inputs are obtained from weak evidence, the range of model inputs is wider, so the differences in rewards between probabilistic and deterministic analyses can be larger. Therefore, weak evidence generally leads to greater or equal life years and Cowley compared with strong evidence. We conducted a simulation study to assess the bias and accuracy of probabilistic versus deterministic analysis in a Markov model. The estimate of interest is the total reward, life years, over 100 cycles, interpreted as the expected survival time for 100 years of follow-up, generated by the deterministic and probabilistic analysis for the Markov model. The main performance measures are biased and mean square error of the rewards. This slide shows the process of assessing the bias and accuracy of probabilistic analysis versus deterministic analysis in Markov model in this simulation study. We considered 3 scenarios with different cohort sizes, n equals 100 as weak evidence, n equals 500 as moderate evidence, and n equals 2000 as strong evidence. Results of this simulation study were presented in this table. Although the simulation generated unbiased estimates of transition probabilities, both deterministic and probabilistic analysis overestimated the reward. Further, the probabilistic analysis is associated with larger bias and mean square error than the deterministic analysis. The bias and mean square error reduced as the sample size of the binomial data increased. When the hypothetical cohort size was large, 2000, in the case of strong clinical evidence, the bias in both analyses was small. However, when the sample size of the hypothetical cohort was 100, in the case of relatively weak evidence, the bias in both analyses was large. In particular, the bias in the probabilistic analysis was even larger. Probabilistic analyses estimating Cowley are likely to lead to greater bias compared with deterministic analyses. For the bias of disease cost, it is involved in more parameters, and is likely to be case by case. We used a simulation study to evaluate the impact of time horizon on bias in a Markov model. Time horizon may substantially impact the cost effectiveness in economic evaluations. Wisloff and colleagues reviewed cost-utility studies published in 2010 and found the magnitude of Cowley gained was strongly associated with the time horizon. The mean Cowley gained was 0.04, 0.17, and 0.43 for studies with a time horizon of is less than or equal to 1 year, between 1 and 5 years, and greater than 5 years, respectively. Kim's review found that for studies with multiple time horizons, the extension of the time horizon yielded more favorable cost-effectiveness results. Currently, most economic evaluation guidelines recommend applying a long-term time horizon to capture the long-term cost and effectiveness. However, the accuracy of outcomes derived probabilistically in a long-term model versus a short-term model has not been well investigated. We conducted a simulation study to examine the impact of time horizon on bias for life years in a Markov model. The simulation study showed that bias dramatically increases as the time horizon increases. This figure shows the reward for different time horizons, the number of Markov cycles. In brief, the bias, which is the difference in reward between the deterministic or probabilistic analysis and the true value, dramatically increases as the time horizon increases. Note that the increase is not proportional. Given a time horizon of 20 cycles, the biases from the deterministic and probabilistic analyses were 0.19 and 0.38, respectively. Given 50 cycles, the biases were 1.57 and 2.91, respectively, and given 100 cycles, the biases were 3.73 and 7.21, respectively. In summary, when the evidence is weak, a Markov model run over the long term is often associated with large bias and overestimates the reward. Now, I provide a summary of key messages. The average life year rewards and Cowley in a probabilistic analysis are generally larger than in a deterministic analysis. Based on the same expected values of transition probabilities, weaker evidence results in larger life years and Cowley compared with stronger evidence in a probabilistic analysis. Bias and mean square error of calculated rewards, life years, are generally smaller in a deterministic analysis than a probabilistic analysis. Bias and mean square error reduce as the sample size increases in both deterministic and probabilistic analyses. When the evidence is weak, longer time horizons are generally associated with substantially increased bias and overestimate the life years in both probabilistic and deterministic analyses. Researchers need to balance the potential benefits and limitations of a long-term model to select the appropriate time horizon in Markov models. Here is the timeline of this article. Thank you.